In this video, we'll look at examples of charged particles moving in existing electric fields. Instead of looking at the electric force exerted on the charged particle due to electric fields, we'll look at the work done by the electric field and the change in potential energy that the particle experiences in the electric field, and additionally, the change in electric potential or voltage that the particle experiences. So let's take a look at this first example. I'll read it for you. High energy ionizing radiation in the Earth's atmosphere causes electrons to be freed from air molecules and results in these free electrons in space surrounding the Earth. So an electric field additionally exists in our atmosphere. The static fair weather electric field is approximately 150 volts per meter near the Earth's surface and drops exponentially to 1 volt per meter at 30 kilometers in altitude. So that's some information for you. The Earth's surface accumulates a positive charge, so the electric field is pointing upward. And that's a key piece of information near the Earth's surface, that the electric field is pointing upward. So we'll just highlight that. Electric field is pointing upward. Near the Earth's surface, it's approximately 100 volts per meter. So now we have our information about the electric field. It's also estimated to be uniform near the Earth's surface, just like our gravitational field. An electron is released now from a position of rest in this space and is forced to move downward, so we know the direction of the motion. We know it's an electron, so we know the charge of the particle. And downward through a distance. That distance is 120 meters. We want to know what is the change in electric potential energy. That's the electron's change in electric potential energy in that field. What is the change in electric potential or voltage between the 2 points? And what is the downward velocity of the electron at this downward distance? So let's set up this problem. Once we've read it, we've highlighted what are the key pieces of information. We'll pull them out as to what we're given. We're given the magnitude of the electric field, and I wrote that as a vector. So it's downward, right? If it's a vector, it has to have a direction, so we can use downward as our direction. Actually, I guess it's upward based on our diagram. So it's upward, and then we can draw our arrow representing that. We have a distance of 120 meters. I also write that as a vector. There's our downward, right? So the vector means we also have to have a direction. So that's downward, or we could just represent it as this arrow. And we know we were given the initial velocity of the electron was at rest. We can add what we know to, we have our charged particle in this, moving through this distance. What we know that is the force due to the electric field on this electron is in the direction of its motion. So if the force on the electron, if the motion of the electron is in the direction of the electric force, then the electric field should be doing the work on that particle. We want to find the change in potential energy. If the electric field is doing the work, we expect a decrease in potential energy. We want to find the change in electric potential. That electric potential is potential energy per unit charge, so we expect a decrease in electric potential, or do we? Because it's change in potential energy per unit charge, and our charge is negative. So perhaps we're going to get an increase in electric potential. And then we can find our final velocity of that electron once it moves through that distance. In order to do that, we're going to have to apply our work energy theorem and conservation of energy. And we can do that because our electric force is a conservative force. So our theory that we can start with, that our potential energy is the negative of the work due to the system. Our system here is the electric system. Our work is the line integral of F dot ds. It's the negative of the work, so it's negative of the line integral. And then we can substitute in for electric force the charge times the electric field. So here's our generic theory. From our generic theory, again, what we can write up here for our given is that Q is equal to negative E, where E is our elementary charge, and since it's an electron, it's negative E. Although we drew it in the diagram, now that we have our theory, we should write that up there to make sure we recall it. And We can continue then. There's our theory that we will need. We'll also need our potential theory, electric potential, this potential energy per unit charge. So we can just divide out the charge here, and that's our negative of our line integral of E dot ds. So we can use this, either of these two, as our theory for electric potential. They're all in fact one potential, and we see it's not electric potential, it's change in electric potential, our final voltage minus our initial voltage, and that's what that delta means. And then we can use our work energy theorem that all the work done in a conservative system represents a change in potential, or excuse me, in kinetic energy, and our change in kinetic energy is 1/2 of the mass times the difference of our final velocity squared minus our initial velocity squared. So if we don't recall that theory, it's time to recall it and keep it in memory. And then, for our theory, I guess we're using our charge on an electron, negative E, and the mass of an electron. We'll need the mass of the electron if we're going to use our kinetic energy. So these theories have in it the potential energy that we're looking for based on our givens, the electric potential we're looking for based on our givens, and the final velocity we're working for based on our givens. We're given that it's an electron, so we'll pull out here and we'll write down our mass and our charge for the electron. So then we can go ahead and solve it once we've come up with some theories that we can in fact use our givens to solve for what it is we need to find. So when we're doing our line integral, we have to set up our limits of integration. And so we know the magnitude of the distance is d, or 120 meters, and we're saying final minus initial of d minus 0, where in fact if this was 0, this would be position d up here. But we've handled the fact that we're saying the cosine 180 degrees. So we've looked at our E dot ds, that's giving us the cosine of 180 degrees. So we're going to, since that's handled there, we'll do our d minus 0. And then when we do this line integral, the cosine of 180 degrees will give us the negative 1. And this we're just going to, our elementary charge and our electric field, our uniform, can be pulled out of the integral. So this integral of ds just becomes d. Substituting in for our all of our givens, we can solve that we do end up with negative to 3 significant digits, 2.88 times 10 to the negative 15 joules. We're going to round that to 2 significant digits because what we're given here, 150, 120, the question becomes, is that 2 or 3 significant digits? We're going to assume that's just 2 significant digits. It's not given in scientific notation, so we can't really tell if that's 2 or 3 significant digits, but we'll round our answer to 2 significant digits. But when we go to find the change in potential, which is based on the change in potential energy, we'll use this theory here since we've already done this integral. We will plug back in our 3 significant digits, so we have an additional significant digit when we do our further calculations. And we solve that we do end up with an increase of potential or voltage, which is a joule per coulomb. So we can change that to engineering notation, so it's 18 times 10 to the third, or 18 kilovolts. So then again, that makes sense. What we see that we have an electron moving in the opposite direction of the electric field, moves in the direction of potential increase. When it's moving in the opposite direction of the electric field, it moves in the direction of potential increase, because electric potential decreases in the direction of the electric field, if we recall that from past videos. Alright, so now let's solve for that final velocity. We go and solve for our final velocity. Then we're using our work energies theorem. The negative of the change in potential energy is equal to the change in kinetic energy, 1/2 our mass times the difference of the velocities squared. So plugging in for our givens, we're going to have to do a square root. We needed to remember at rest was 0 initial velocity. So we do our square root. We do end up with a plus or minus. we're going to use the positive velocity because what we're solving for here is the magnitude of velocity, right? We're not solving for the velocity vector, we're solving for the magnitude. We do end up with a negative change in potential energy underneath our square root. Well, that's fine because we solved for a negative. For the change in potential energy is negative, so that gives us a positive, and here we have a final velocity of 8.0 times 10 to the 7th meters per second. So again, if we go back and we analyze our solutions here, we do have a potential energy decrease as the electron moves in the direction of the electric force. That's always the case. If the system is doing the work, there will be a potential energy decrease on that system. What's interesting here is the electric potential. Since we have a negative charge, the potential is going to increase because we're moving in the opposite direction of the electric field. That's something that doesn't happen with gravitational fields because we only have positive masses. But we do have the fact that we have a negative charge. It's being worked on by the electric field. As the electric field is doing the work, we go in the direction of potential increase or voltage increase, even though the potential energy is decreasing. We do come up with a final velocity that's very large, but the acceleration, you can calculate that, the acceleration of the electron is also very large. And that's the case because the mass of the electron is so small. All right, let's take a look at another example. But in fact, to keep the video short, we'll take a look at another example in the next video.